Okay, what I would like to talk about in this presentation is how I can use a right-hand sum with infinite number of rectangles to get the exact area under a curve. So I'd like to talk about the formula and use an example to show you where that formula comes from piece by piece. So first of all, here's the formula that we're looking at, and this is a right-hand sum. Let me blow it up just a little bit so we can talk about it. And that's showing that the right-hand sum area is going to be the limit as n approaches infinity, sigma from I equals 1 to n, and n is the number of rectangles. So we're talking about infinite number of rectangles. And each element of my summation is given by this formula here. And let me put it in red. And where does this formula come from? So let's talk about that for just a second. Okay, so if I was going to calculate the area of this picture that you see right now, that is a right-hand sum of rectangles, there are 6 rectangles. And what I'm going to have to do is look at the width and the height of each rectangle. So you might want to notice that every one of these are connected to the graph of the function, and my function is 1/4 x squared. So if I talk about this point here and this point here, what I can actually see visually is an average rate of change on the graph, which would be change in y over change in x, rise over run between 2 points. We call the run aspect delta x. So that goes back to college algebra. So on an average rate of change, the change in the x value, delta is the Greek letter for d. D is for distance. It is the distance that x moves from one point to the next point. So each one of these is that same distance, delta x, and that is the width of each one of my rectangles, the distance we travel from one point to the next point on the graph. So each one of these rectangles, again, has 2 dimensions, a width and a height. So if we looked at any one of these heights, that's going to be an output of the function for some, I'm going to call this, just right now, some output. And the question is, what y value do we start with? Well, okay, let's talk about the very first rectangle. Notice this is my value, a. So the height of the rectangle, however, is not f of 1. In this case, I have to figure out how far I moved over. So let's do that calculation. How big is delta x? And if I know what delta x is, I know what to plug in here for my first x value. So step 1, let's calculate delta x. Every one of them has to be the same size. So when I look at that, well, okay, I've got 6 rectangles, each one of them of equal length. And those 6 rectangles happen between the distance of 1 and 4. That's what we were given. So that's a total distance of 3. And how did I get that? I took 4 minus 1. But that's not how big each rectangle is, because I have a total distance of 3 units on the x-axis, and I'm going to divide that by the number of rectangles. So each rectangle is going to equal 1/2. And again, I got that from the 3 divided by 6. And let's think about that, where that 3 came from. That was the total distance I traveled in x by taking the end value minus the beginning value. That's where the 3 came from. I started at 1, I ended at 4. That's a total distance of 3, but I need to cut that into the number of rectangles. And again, in formula, that is the b value minus the a value over the n value. So this is where delta x comes from. That will be my precise size of each rectangle. So how far it is from B to A divided by how many rectangles I'm going to plug in there. Okay, so this is helpful because let's think about that. Once I know that amount, I'm going to give myself some room to write here, I can find this y value here. This is going to be f, not of 1, but of 1.5. And that'll give me my very first rectangle's height. So I didn't start at A, but what I did have is A moved over exactly 1 unit of delta x, 1 width, because that's 1 width, and the next rectangle is going to be 2 widths, and the third rectangle will be 3 widths over, and each one of those widths is a delta x. So for each rectangle, the area of each rectangle, it's going to be its height times its width, and more precisely, that height is going to come at not the a value, because it's going to be past that. It's going to be right of it. It's going to be right of it a delta x. So I need to add a delta x for the first one, and then a delta x for the second one. So if I'm just looking at the first rectangle, it'll look like this. If I look at now the second rectangle, so this is the first rectangle. The second rectangle, notice I had to move over 2 delta x's. So its height is, I could either write it as 2 times delta x, that's fine. That's its height times its width. And the third rectangle, again, I'm going to have moved over a total of 3 of those delta x's. To find its height, then, that's an ugly looking delta, sorry about that. And again, times its width, so its height times its width. And we begin to see a pattern forming here. First rectangle is 1 delta x over. Second rectangle is 2 delta x's over. The third rectangle is 3 delta x over, which means the area of the nth rectangle, or any of them, is going to be, actually I'm going to put the ith rectangle, sorry. Is going to be a plus either I times delta x, or many times written as delta x times I. Again, I'm going to multiply by how many rectangles I've gone over. So that's the area of each and every single possible rectangle. I've explained how we calculate delta x. And now I would do this if there was 5 rectangles. I would go from 1 to 5. if there were 7 rectangles, I would go from 1 to 7, and then I would add them up. So the general formula is starting at 1 and ending at the nth rectangle. Each rectangle's height times its width could be properly represented by this for a right-hand sum of exactly n rectangles. But what's interesting is we said that the more rectangles, the more accurate. So if I actually wanted to find the true area of this function using this right-hand sum, I would have to take the limit of it with infinitely number of rectangles. And we're going to get to how this can be done with calculus techniques a little bit more advanced, but this is my notation for the exact area using infinite number of right-hand sum rectangles to calculate the area under a curve.